Hello everyone, welcome back. Today we're going to talk about power. Now, since this is another term that we use in our common everyday language pretty often, I'm going to bring up an example in order to explain how it's used in a physics sense. And to do that, I'm going to use this image. Now, what you're looking at is an event from something that is called the World's Strongest Man competition. What they do is try to find the strongest men they could find on Earth, bring them all to one spot, and have them do a bunch of competitions to see who is the strongest. Now, this particular event is called the Atlas, and here's how it works. There are 5 columns, and in front of each column is a stone sphere. You see this gentleman has already put up 4 of them. Originally, the spheres are laid out on these holders you see on the ground. The job of the athlete is to run up and one by one lift the spheres onto their pedestals. Now, this picture only shows one athlete, but this competition is usually done head-to-head, so there's a second one somewhere here on the side. Now, you can win this competition one of 2 ways. Either the first person to put all 5 spheres on the pedestal wins, or in case neither of them do, whoever puts the most spheres up. Now, something that's interesting about this competition is typically around the 3rd sphere, you can usually tell who's going to win. Although there have been upsets, here's what usually tends to happen. So the spheres are the exact same mass for each athlete, and the towers are the exact same height for each athlete. Typically, around the 3rd or 4th column, this tends to happen. Athlete A grabs a sphere, athlete A grabs a sphere and lifts and goes and puts it up. Athlete B will grab the sphere and put it up in much less time. Now, let's take these 2 situations, what I just showed you, athlete A and athlete B. My first question is, who did more work in this situation? I'll let you use the columns to get some space. So, work is how much energy is transferred to the system. And the system is the sphere and the Earth, because the sphere starts at rest on the ground, ends up at rest on the pedestal. So there's no kinetic energy involved from initial to final. It's all gravitational potential energy, which means work is change in gravitational potential energy is mg delta H. Well, the mass of the spheres for both athletes is the same. Gravitational pull certainly isn't different for either of them, and the height of each pedestal is the same. So, the question being, which of these 2 individuals did more work? They both did the same amount of work. Side question, who's most likely to win the competition? Well, athlete B would be most likely to win the competition, which now raises another question. Which one of the 2 examples I just gave would be the more powerful individual if they both did the same amount of work? Well, the second athlete would be the more powerful individual because the second athlete did the same amount of work in less time. That's the key here. So in physics terms, power is not about how much work can be done, it's how quickly that work can be done. So athlete B would win the competition because he could raise the sphere up onto the pedestal in less time. That therefore would make him the more powerful individual. So that means we are going to use this as our power definition. Power, the rate at which energy is transferred over a period of time. Now, if you notice, we have energy is transferred in this definition. And technically, this should be energy transferred to or from the system over a period of time. And energy transferred to or from the system is, of course, work. So power, therefore, is work divided by time. And remember, work was the second most important definition in the course. Now, I'm going to move this on the side because there's something I want to show you while we're here. If power is work over time, work is force parallel times displacement over time. Do you recognize what I just circled? That is actually the first equation that we derived, and that was average velocity. So something to note, just like for work, you need a displacement and you need a parallel force here. Power just involves a time element. So the symbol for power is a capital P, which thankfully is one of our symbols that actually makes a lot of sense. The unit, well, looking at our equation here, the base unit for power is joules per second. Now, before I say what I'm about to say, any AP grader or physics teacher will accept this as a unit for power, or at least they should, because this is the actual unit for power. It is the rate at which energy is transferred. So it's literally how many joules are transferred to or from your system per second. That being said, this is a unit that was given its own name, just like Newton's was. The shorthand version of the unit is called the watt. abbreviated W. Not to be confused with work, because work is a label and watt is a unit. So at least for a while, I actually recommend you use joules per second just so you can see the cancellations. But if power is ever given to you for a problem, it is almost always going to be given to you in watts. I'll put the equation in the corner here so we can reference it. And there's one more thing that I would like to show you. Depending on what country you're from, you may be familiar with watts as a unit of power for electrical devices like light bulbs and such. But this could be used for anything. That being said, in America, there's another unit used for power pretty often, typically with vehicles, and that is horsepower. And just to give you the conversion, 1 horsepower is approximately equivalent to 746 watts. So when we say a vehicle has 200 horsepower, that could very easily be translated to watts if we wanted to. Okay, let's do a few problems to get the idea across. A 45-kilogram boy climbs a vertical 6-meter rope with a constant velocity. His power output is 157 watts. How long does it take him to climb the rope? I'll start with my givens. Mass 45 kilograms. Delta Y 6 meters because he's climbing a 6-meter rope. Power is 157 watts or 157 joules per second. We are looking for time. Now, just to note real quick, if I was to make a bar graph here, it would go from work to gravitational final. Now, technically, since I said there's a constant velocity, I would have some kinetic on both sides. But since the velocity is constant, I know those two kinetic energies will cancel. So I'm going straight from work to gravitational potential energy. Now, power is work over time. Now, there's a reason why I keep saying work is the second most important definition of the course, and that's because very often the definition will lead you to where you need to go more than the equation. In this case, work is a transfer of energy to or from the system. My system is the boy and the earth, which means the energy being transferred into the system is gravitational potential energy. So it's changing gravitational over time. Changing gravitational is mg delta y, and I'm looking for time, so I'll rearrange this for time. 45 kilograms times 9.9 newtons per kilogram times 6 meters over 157 joules per second. Kilograms cancels. Parallel newtons times meters is joules, so they cancel. This flips because it's in the denominator, and I get seconds as my answer. And I will get 16.85 seconds. So all power really is just a better understanding of work. If you have a good understanding of work, power is just work with time involved. And the big key here is recognizing your energy transfer was gravitational. Once you have that, just start with your base equation and just keep expanding it. Okay, let's try this one. A 3,600 kilogram car starting from rest reaches a speed of 60 meters a second in 13 seconds. Assuming there is a constant frictional force on the car of 150 newtons, what is the power output of the car? I'll list my givens. Mass 3,600 kilograms, VI is 0 meters a second, VF is 60 meters a second, time is 13 seconds, and the frictional force 150 newtons, and I could already tell my system here is just the car. This looks like a drag race, and if the car is gaining gravitational, this driver has a very big problem. Now, I'm going to solve this 2 ways. First, I'm going to do it from the point of view from this equation. I have my bar graph, I have no initial, final, I definitely have kinetic energy, and come to think of it, I'm going to have internal because there's friction involved, which means the car just can't be the only thing in my system. I'm going to assume the frictional force is from air drag, so I'm going to add the air to my system. Doing this is just like when we added the ground to our system earlier. And I'm adding internal because I know I want it separate from work. The energy transfer is coming from outside the system, and I need the work for my power equation. This gives me 1/2 mvf squared plus force friction delta D. Now I have mass, I have VF, I know VI is 0, I have force friction, I don't have displacement, but I have 3 kinematic givens. And if you ever see things like VI, VF, time, acceleration, you're probably going to use kinematics in one form or another. I will use our first kinematic equation, 1/2 there's no VI plus 60 meters a second times 13 seconds, gives me a displacement of 390 meters, which I will add to my givens list now. And as a side note, this is a little under 1/4 mile. I will now do this, 1/2 3,600 kilograms times 60 meters second squared plus 150 Newton times 390 meters. This gives me 6,538,500 joules because it's still work. Power is work over time, gives me this big number over 13 seconds, gives me 5.03 times 10 to the 5th watts, or joules per second. Okay, in this example, I used the work over time relationship. So I made my bar graph to find out where the energy is. Notice my bar graph is what tipped me off to the fact that I should have internal here. Found all the energy transferred and then divided by the time. Now I want to show this to you using another method. I'm going to keep my givens list because we have them and we can very easily find displacement. but this time I'm drawing a force diagram. I have force earth and force normal, but I know they're going to cancel, so these do not concern me too much. I have force ground on car, which accelerates the car forward, and I have force friction, which I know is 150 newtons. Now, this time, I'm going to get the single most important definition of the course, acceleration, which is a change in velocity over a period of time. 60 meters a second over 13 seconds gives me acceleration of 4.62 meters per second squared. Now, I am doing this because my goal is to find this force. Since this is the force needed to accelerate the car, this is force parallel in my work equation. F net would be force ground on car minus force friction. Therefore, force ground on car will be F net plus force friction, which would be mass times acceleration via Newton's second law plus force friction, which would be 3,600 newtons times 4.62 meters per second squared plus 150 newtons. This would give me 16782 newtons. Velocity average would be 1/2 VI plus VF. Since VI is 0 and VF is 60, that means average velocity would be 30 meters per second. So force ground on car, which is accelerating the car forward, is my force parallel. The car exerts a force on the ground, and the ground exerts that force back in order to accelerate the car forward. And this is the force needed not only to accelerate the car, but to overcome the frictional force. I also have the average velocity, which means I can now use the other version of the power equation, 16782 newtons times 30 meters a second. Now, if you look at the units, it's newtons times meters, which is joules over seconds, which is 5.03 times 10 to the 5 watts, or joules per second. So I get the exact same answer we got using the other method. Just a side note, there's a typical question that is asked that involves a situation like this where someone's pushing a box or something, and the box is moving at a constant velocity, and they give you the frictional force, and ask you what the power output of the person is. Well, if it's a constant velocity, you just need the force he's pushing, which would match friction, times that velocity itself, because a constant velocity is an average velocity. And one more thing, this is about 674 horsepower, which is much more powerful than the average vehicle you'll see on the road, but less powerful than a professional sports car. So very quickly before we finish, this last problem can be solved two ways. One way is purely looking at energy. I made my bar graph, I found out how much work was done, divided by the time to get the power output. Or I can look at it through forces, create a force diagram, get what the parallel force is, get my average velocity, and solve for power using this method. Keep both these methods in mind because sometimes you will be given givens on purpose that makes one way shorter than the other. And on timed assessments like the AP exam, how quickly you can do a problem comes into play. All right, I will end this here. Have a good day. This is Mr. M signing off.